So now let me introduce our operating system stuff. It's called IHK MC kernel. And so IHK is a Linux kernel module, and that's capable of the interface for heterogeneous kernels. So our assumption is our operating system will run on the many core architecture. And so on some so this picture shows the one single compute node. And so there are many the cores, and on some cores, the Linux kernel is running. And the HPC applications run on the rest of the cores. So that's our assumptions. And so the IHK partitions the hardware resources like CPU cores and memory. Okay? And so IHK enables to run the lightweight kernel on those cores, and also the communication between Linux and this lightweight kernel. Okay? And we assume the full Linux kernel is running on those cores, and so our system daemons are so running on this Linux kernel using those cores. And some institute non-HPC application might run on also this Linux kernel. And so device drivers handled by the Linux kernel. Okay. And so here is a lightweight kernel running. And so our lightweight kernel is called MC kernel. And so MC kernel is a lightweight kernel that's designed for HPC and noiseless, and it's a very simple the structure. And so it's sorry. So we implement just the performance sensitive system calls such as process memory management and signaling stuff, and the rest of the system calls of the Linux API, those are offloaded to Linux kernel. And so glibc and some pseudo file systems like /sys or /proc, those are implemented on the MC kernel. And so the same binary of the Linux may run on here without any recompilation. So in that sense, actually, so from the user's viewpoint, so MC kernel is it's invisible, and it's transparently to the Linux kernel, the features are visible, okay, from the HPC application. And the IHK MC kernel runs on Intel Xeon and Xeon Phi because we don't have the post-K architecture so far. And so we have been implementing this operating system on Intel machines. And also the Fujitsu FX10 and FX100. So those are the successors of the K computer. So IHK MC kernel runs on also those supercomputers. But it's based on Spark architecture, and that's the kind of the experiments. So this slide shows how we deploy the IHK MC kernel. So we assume the Linux kernel is a resident, and it has the IHK kernel module. And so again, so the daemons running on Linux kernel. Okay. And so IHK enables to reload MC kernel dynamically, and it's not required the hardware reboot. And so our assumption is so application what kind of the operating system features application needed. That depends on the applications. And so, for example, so application A doesn't require the process thread scheduling. So that's because the application creates the same creates the processes and threads that's exactly the same number of the CPU cores. So in that case, so the application doesn't. So those processes are just running on the physical the cores without any schedulers is required. And so the CPU or process scheduler is one of the big the OS noises. That means so disturbing the application execution. And so such kind of application so runs on the MC kernel without the scheduler. Okay. And so when the application, another application, but requires the scheduler, that's because the many processes or threads more than the physical CPU cores the created. In that case, so CPU scheduler is required. And so in that case, the MC kernel with scheduler is invoked with this application. Okay. And after that, then after the finishing the application, the execution, then return back to this state. And of course, application is not the HPC application, and it's want to use the full capability of Linux kernels. And then so all cores are used for Linux kernel, and applications run on this Linux kernel. Okay. So this is our scenario of the IHK and MC kernel. So now, I will show you the evaluation results. So this slide shows the result of fixed work quantum benchmark. It's from the Lawrence Livermore National Laboratory. And this benchmark shows how much operating system disturbs the application execution. And so this so this is a result using Linux kernel plus ISOL CPU's the configuration. So that means all the system daemons activities are running on the core, and that means the application cores for application doesn't include the activity for system the daemons nor the threads, and so x-axis is the number of the this benchmark trials. So because when the benchmark runs, so because it consumes just a fixed amount of the CPU time without any the I/O, and so if no CPU noises happen, then the execution time must be the same. So that means must be fixed, flat. But here, so we see the several the variation. So this is the execution time in the cycle. Okay. And so here, this is the MC kernel. So you see, so it's flat. So that's because the OS doesn't generate any noises for disturbing the application execution. So MC kernel, IHK MC kernel, actually, so this is a result of using the Xeon. And IHK MC kernel runs on the Intel Xeon 5 night running. And we are planning to deploy the IHK MC kernel to the Oak Forest, the PAX supercomputer. That's installed at the University of Tokyo. And it's operated by the University of Tsukuba and the University of Tokyo. Okay. And so that's the 25 petaflops MP. Okay. And so this slide shows the result of the GeoFEM benchmark. That's the ICG with additive Schwartz domain decomposition. And it's we take the weak scaling. And so this is the number of cores, physical cores, and this the higher is better. And we see it's the IHMC kernel performs better than the earliest kernel. Okay. And so actually, so this result is a little bit old. Actually, it's mostly, actually it's maybe 1 year old. And so latest results will be presented at this year's IPDPS by Balazs Gerofi. He's my colleague. And so important thing is that this is done using the same binary. That means the applications, this GeoFEM benchmark was compiled under the Linux kernel. And the same binary runs on the Linux kernel, of course, and also the MC kernel without any change. Okay. And this is the result of the CCS QCD. That's the QCD application code. And again, it's the weak scaling. And using the same machine, Oak Forest PAX. And again, so we got the better performance than the Linux kernel. Okay. And so this is the result of the MiniFE. It's from the Coral benchmark suite. And that's the conjugate the gradient. And it's this is a case of the strong scaling. And again, higher is better, and we got the much improvement, okay, in scale this strong scaling case. So maybe 2 more slides, I think. So now, I'll explain the ongoing R&D. And actually, I said the performance, the critical, the system calls are handled by MC kernel, and the rest of the system calls, Linux system calls, are offloaded to the Linux kernel. So usually that works because the HPC application, mostly the computation and the communication, not the other system calls, the non-system calls are involved. Of course, the file I/O should be involved, but and in most HPC, the communication, the hardware, like the InfiniBand and the K computers TOEFL interconnect. So those devices, in those devices, we can access the hardware registers in the application level. That means, so whenever the application needs to send or receive operation, then those operations do not involve system call. Just the issuing commands to the registers of device drivers. So that's the case in the InfiniBand and the TOEFL. But so unfortunately, in the Intel's interconnect, it's called OmniPath. So it requires the system call. And so that's why, so in that case, so that's why, so here is the result of ping pong, the benchmark, and the x-axis message size, and then the y-axis are the bandwidth. And so this is the MC kernel, and the blue line is the Linux. So Linux is much higher performance than the MC kernel. That's because in MC kernel, each send and receive operation, the system call is delegated to the Linux kernel side. So that's overhead is the source of the differences. And so what we have done is, of course, those drivers are also ported to the MC kernel. Then, so the same performance might be achieved, but it has a much the time-consuming the processes, and so instead of that, so we decided to provide the mechanism for porting the partial device driver source code to the MC kernel. And so that's actually the MC kernel provides the same internal the API for driver and of the Linux kernel, and so that the partial the source code can be ported to the MC kernel, and also actually so the MC kernel, so Linux kernel has of course its own the memory management and function, and the Linux MC kernel has the own the memory management. Okay. It's separated, and our physical memory management is much efficient than the Linux kernel, and so what's happened is so this is a result of using the partial Linux drivers, and so we got the much the higher bandwidth than the Linux kernel now. Okay, and so that's the current the ongoing R&D. But still, so we have the issues actually, and so now my colleagues have been figuring out so what's wrong. Okay. So we hope this new feature will be deployed to the Oak Forest Park's machine. Okay, so now I will summarize my talk. So the system software stack for post-OK so is now being designed and implemented with the leverage, but actually so international collaboration. I haven't explained what kind of the collaborations have been done in within those laboratories, but we have been collaborating with those the research institutes. And we will open the software stack developed at the RIKEN. Okay. And so, of course, the target is the ARM architecture. But we also support the Intel Xeon and Xeon Phi. Okay, that's all. Thank you.
Thank you very much.